So here we have a very sweet and simple numerical. Let's read the statement first. 1 gram of a gaseous compound of boron and hydrogen occupies 0.82 liter at 1 atm and 3 degrees Celsius. The compound is okay. You have option A, B, C and D, and you have to figure out which is the correct formula of the gas that we are talking about in this particular question. So you are given volume in liter, pressure in atm, and temperature in degrees Celsius. Let's quickly convert this into Kelvin. It will be 273 plus 3, which is 276 Kelvin. Perfect. So you have the mass as well. Okay. So if I can see I have volume, pressure, temperature, I just need to figure out what is the molar mass of the gas, and I'll match with the options and I'll get my answer. So if I apply PV is equal to nRT, the pressure is 1 atm, look for the units as well. The volume is 0.82 liter. Moles, I do not have the moles. The formula for moles is given mass upon molar mass. Given mass is 1, and let's assume the molar mass of the gas to be m, right? So moles comes out to be 1 by m. The value of R given to us is 0.082. I can smell some ease of calculation, and the unit is liter atm. So keeping the units of pressure and volume in mind, I'll put it as 0.082 into temperature 276. Perfect. If you just solve this out, 0.82, 0.082 will be 0.1. M will be 0.1 into 27.6. 276, that will be 27.6 gram per mole. Perfect, perfect, perfect. I have 4 options, A, B, C and D. I have to figure out their mass. So boron is 10.8 plus 3 hydrogen. No, not 27.6. Boron 4. So 10.8 into 4 will be 43.2 plus 10. No, not matching with what I have calculated. B2H6, boron 10.8 into 2 will be 21.6 plus 6 hydrogen. Yes, this is what is 27.6. So, and we have also calculated the molar mass of the gas is 27.6, which is option C. I guess option C is matching. Let's look for option D as well once. Boron B3H6. So 10.8 into 3, so will be 38, 324, 32.4 plus 12. No, going far away. So option C is exactly matching with what we have calculated. The molar mass is coming out to be 27.6, which is matching with B2H6. So B2H6 is going to be the correct answer to this. So here you have a graphical question. Let's see what the question is saying. The curve shows Maxwell's distribution of velocities with increase of temperature. Okay. You have this curve, which is in between number of particles and speed, and the blue one denotes the cold curve, and the red one is for hot. That means you are increasing the temperature becoming from cold to hot, and the curve is changing its shape. Okay. What else is there? Okay, you have 2 statements. Let's read the statement. Statement 1 says most probable velocity increases. Most probable increases. Okay. The statement 2 says fraction of molecules possessing most probable velocity decreases. Okay. And the option says statement 1 correct, 2 incorrect, 1 and 2 both correct, 1 and 2 both incorrect, or 1 incorrect, 2 correct. Options has to be read carefully. Okay, these are jumbled options, right? Fine. So let's talk about the statement 1 for the time being. It says most probable velocity increases. See, let's say that we are going from T1 to T2 and we are increasing the temperature, right? So the cold graph, the blue graph, is for T1, and the hot graph is for T2, right? Okay. If you observe the graphs carefully, you are increasing the temperature, and what happens to the most probable velocity? The very first question is, just by looking at the graph, can we figure out where is the most probable velocity? Very well, we can do that. See, if you observe this point, and for this hot graph, this point, these are the most probable velocity for hot and cold. If you talk about the blue, I'll call it as V cold, and for the red one, I'll call it as VH. On the graph, I have shown you the velocity which is the value of most probable velocity. Now it is clearly visible that V hot is higher as compared to V cold, or we can say that VT1 or VT2 is higher than VT1. Make sense? The cold is T1, the hot is T2. So T2 is greater than T1. So as you are increasing the temperature, the most probable velocity. See, if you increase the temperature, the motion of the particles, the rapid motion is going to increase, and that's why the most probable velocity is also going to increase. And how am I going to figure out this is the most probable? You can observe carefully from the graph itself that corresponding to these velocities, the number of particles or the fraction of particles is maximum. That is why these are the most probable velocities which are increasing on increasing the temperature. Let's get back to the statements again. The most probable velocity increases, yes, on increasing temperature. Most probable velocity increases. This is perfectly true. Fraction of molecules possessing most probable velocity decreases. Now if you observe this is the fraction of molecules, right? When you are increasing the temperature, when you are moving from T1 to T2, the value of fraction of molecules is coming down. And why this is happening? See, the area under the curve, that gives you the summation of fraction of molecules with different velocity, and the area under the curve, that is the number of particles, is going to be same. You are not increasing the number of particles, you are just increasing the temperature. So if molecules having velocity, the most probable velocity is increasing, obviously the number of fraction of molecules is going to come down, which is clearly visible in the graph itself. If you number it as N1 and N2, as you are increasing the temperature, T2 is greater than T1, you are increasing the temperature, N2 is becoming less than N1. This is what is visible in the graph. So let's get back to the statement. Fraction of molecules possessing most probable velocity decreases. This is also perfectly true. So both the statements are true. So can I say that statement 1 and statement 2 both are correct? Option B is going to be the right answer to this question. Here we have a numerical question. Let's read the statement together. When a certain amount of ethylene was combusted, 6226 kilojoule heat was evolved. Okay. If heat of combustion of 1 mole of ethylene is 1411 kilojoule, the volume of oxygen at NTP that entered into the reaction is. So you have to figure out the volume of oxygen, and the options are, okay, you have different options: milliliter, liter and liter. Fine. Okay, let's quickly write the combustion reaction of ethylene first. But before that, tell me the formula of ethylene. It is C2H4. Do not confuse it with ethine. The common name for ethine is acetylene, right? So it is ethylene here. The formula is C2H4. Let's write the combustion reaction. C2H4 plus oxygen going to react, and it is going to form CO2 and water, right? Quickly balance it. 2 carbon, so 2 will be multiplied here. You have 4 hydrogen, so 2 again. You have 2, 2, 4, 6. 6 oxygen on the product side. So you have to multiply this oxygen with 3. 3 into 2, 6. Perfect. The reaction is pretty balanced. Okay. I have to figure out the volume of oxygen. If I know the moles of oxygen, I can figure out the volume at NTP, right? 1 mole is 22.4 liter. Okay. The task is to first find out the moles of oxygen. And for that, I need to figure out the moles of ethylene, right? And in terms of ethylene, energy data is given to me. So let's read that energy data first. It is like 1411 kilojoule heat will be released when 1 mole of ethylene undergoes combustion. 1 mole ethylene. Right. So you are given 6226 kilojoule heat. It will be released when, can we use the unitary method? Right. So it will be 1411 into 6226 moles of ethylene, right? Let's not calculate it. Let's put it like that only. 6266 upon 1411 moles of ethylene, right? I have the moles of ethylene. Can I read the stoichiometry in the reaction? It says 1 mole of ethylene is going to react with 3 moles of oxygen. Let me write it. 1 mole ethylene is going to react with 3 moles of oxygen, right? Okay. So I have this much number of moles of ethylene. Can I just quickly calculate the moles of oxygen? It will be 6226 upon 1411 moles of ethylene going to react with, multiply by 3, unitary method, 3 into 6226 upon 1411 moles of oxygen, right? Okay. Now I have the moles of oxygen. Half job is done. I just need to calculate the volume of oxygen at NTP. 1 mole oxygen at NTP is equivalent to 22.4 liter, right, of oxygen. And the moles that I have is 3 into, it is 6226 upon 1411 moles of oxygen at NTP. Just by using the unitary method, I can calculate the volume. So it will be 22.4 into 3 into 6226 upon 1411. This is the liter of oxygen, right? If you just observe the options carefully, see, options are very, very far apart. They're not very close. We can take some smart approximation. Let's do that. So can I write 6226 as 6200 and 1411 as 1400 and 00 cancelled, so 14, 62, 14. Can we just cancel it with 2, 31, 7, 7, 4, 28, 7, 5, 35. So 31 will be somewhere around 4.5. Okay. So I have 3 into 4.5. 4.5 into 3 will be 12, 13.5 into 22.4. Okay. Can I just take one more very absurd approximation? I'll write it as 14 into 21. Let's see. See, I have taken approximation in the reverse manner, so that the error gets cancelled somehow. So if you multiply 14 into 21, it will be like 7 into 42, 7 to 14, 28, 294. 294 liters of oxygen. Let's see if we're gonna match it with some 296.5 ml. No. Be careful with the unit. 296.5, and what we have is 294. pretty close. So, of course, option B is going to be the correct answer to this question. Other options are really far apart. This is 6226 into 22.4 liter. Huge number? No, not possible. Option D is 22.4 liter. Again, not possible. So, the correct best option to this question is option B, which is the correct answer to this. So here you have a question on ionization potential. Let's see what the question says. The value of IP1, IP2, IP3 and IP4 of an atom are 7.5, 25.6, 48.6 and 170 electron volt respectively. The electronic configuration of the atom will be, and you are given 4 different options with different electronic configuration. Okay. See, basically what is ionization potential? It is nothing but ionization energy and it is given in electron volt here. Okay. So let's assume that the atom is A. If A loses 1 electron, A plus will be formed and the IP1 value given for this is 7.5 electron volt. Perfect. If second electron is going to be lost, it will be from A plus to A 2 plus 1 electron and IP2 given to is 25.6 electron volt. Perfect. Similarly, we are going to do it for third electron 2 plus to A3 plus. Electron is lost. IP3 is 48.6 electron volt. Right? Okay. For fourth electron A3 plus to A 4 plus 1 electron is lost and IP4 value given to us is 170.6 electron volt. Perfect. See, when you remove first electron 7.5 and after removing first electron to second electron, the difference of energy is like what? You can say 18 electron volt, right? 25 minus 7. And if you move from second to third, what is the difference of energies? Just calculate that. 28, 48, 25. It will be somewhere around 23 electron volt. We are roughly calculating it. Okay, approximate values. After removing third electron, when you are removing fourth electron, this is like what? Somewhere around 120 electron volt. What do I observe? After removing third electron, when you are trying to remove the fourth electron, the energy gap is huge. That means after removal of 3 electron, the atom A must have gained the noble gas electronic configuration, right? This is what we observe from the values given for ionization potential. As you are moving from 3 to 4, you are removing the fourth electron. There is a huge energy gap. You see 120 electron volt is pretty big as compared to 18 and 23. So you have to look for that electronic configuration where valence electron are going to be 3, right? Okay, let's look for it. In first, you have 1 valence electron. No. In B option, you have 2 plus 1, 3 valence electron. Might be. Option C, you have 3 to 5 valence electron. No. And option D, you have only 2 valence electron. No. So, only option B is matching with what we have calculated. So, option B is going to be the correct answer to this wonderful question. So here we have a very sweet and simple numerical from neutralization reaction. Let's see what the question says. 0.45 gram of an acid, molar mass is 90 gram per mole, was neutralized by 20 ml of 0.5 normal caustic potash, that is KOH, the fancy name of potassium hydroxide. The basicity of the acid is, so basically you have to figure out the N factor for your acid, right? Okay. So this is like a neutralization reaction. An acid reacts with a potassium base to form potassium salt and water, right? I have written the general reaction. So in neutralization, the gram equivalent of acid, this is like complete neutralization. So gram equivalent of acid is going to be equal to gram equivalent of base. We have equated the gram equivalent of acid and base, right? I have to calculate the gram equivalent for acid as well as base and put that value in this equation. So I have normality value. See, this is one thing. Normality. The formula for normality is what? Gram equivalent upon volume of solution in liter. So from here I can say gram equivalent is nothing but normality into volume of solution in liter, right? This is one thing. There is one more relation, that normality is equal to molarity into n factor, right? So normality is what? Gram equivalent by volume of solution in liter. What is molarity? Moles of solute upon volume of solution in liter into n factor, right? So if you cancel volume of solution from both these sides, what you get is gram equivalent is equal to moles of solute into n factor. Fine. Okay, so I'll use both the formulas according to what is given to me and try to solve this. So let's do it. So for gram equivalent of acid, I'll use this formula, moles into n factor. What is the moles of acid? The formula for moles is given weight by molar mass. So given weight is 0.45. Molar mass for acid is given as 90 gram per mole into n factor of acid, right? Okay, this is what we have to calculate, the n factor. Gram equivalent of base is normality given 0.5 normal into volume of solution in liter, right? Do not forget that, otherwise we'll calculate the wrong answer. Okay, so we have to solve this. N factor will be like what? 0.90 upon 0.45 into 0.5 into 20 by 1000 is like 1 by 50, right? So if I remove this decimal with 100, 90 by 45, this will be like 2, and what do you have? Like 50 with this 0 and 10 with this decimal, 5 with 5. The only left value is 2. So n factor comes out to be 2, and this is going to be the basicity of the acid. Option C is going to be the correct answer to this question.